Hi, everybody, and welcome to this session on Zoom. Basically, the whole session today is dedicated for Lab 9. That is Ohm's Law. Your instructor felt that it was necessary to do Ohm's Law lab before the actual, at least go through the ideas in Ohm's Law before you guys go into the exam. So that's basically, in part, I guess it helps to do some review with that, and also gives you more time to prepare for your exam. Okay, so let me take, or should we do that later on? Okay, we can do it later on, but I need to do the attendance at some point. Right now I have 13 people. I know that we're missing 10. Okay, that's a lot. Anyway, today's lab, like I said, is on Ohm's Law, and let me share with you the instructions first of all of the lab. Okay, here they are. And so this is Ohm's Law, the lab that you guys are going to be doing. Unfortunately, you're not going to be doing in the classroom, which is really kind of a pity because it's really one of the most interesting labs that you would do in this class, but we're not going to be able to do it. So in part, we're going to do it together right now. We'll discuss the questions, hopefully the answers to them, at least most of them. Some of them you have to do on your own. Then I will show you the links that I already posted on Canvas for you guys to go onto GeoGebra and basically pull your data for your tables. Now, notice the following. The instructions will change in a sense that the steps onto the 1, 2, 3, 4, you will have an update, hopefully no later than tomorrow afternoon, tomorrow evening. You will have an updated version of the instructions on what to do. Today, we're going to talk about the things that we need to do for this lab. So basically, that's the idea behind it. So Ohm's Law, did you guys do it already in lecture or not yet? Did you do Ohm's Law or not yet? I need some feedback quickly. Oh, but you guys don't remember that? Okay, so let's talk about that in here to try to understand it then, what that is. And then let me pull another screen then. So this is my whiteboard, basically the one I write on all the time. And so what is Ohm's Law? Basically, it has to do with circuits. You know that there are basically two kinds of materials. There are more than two kinds of materials, actually. There is a lot. There is the conductors and insulators. So those are the two basic types of materials that we encounter on a regular basis. So in a conductor, by definition, basically conducts electricity. So there are two types of materials: conductors and insulators. So what is the difference between the two? In the case of conductors, which are really mainly metals, but you have some alloys also that can conduct. That basically, and some different, basically, how should I put it, compounds, not necessarily metals, that conduct electricity. So what happened in this case is that they have free electrons. Electrons, not really free electrons, I should have communal electrons, electrons that belong to the entire community of the atoms. They are not tied to a specific atom. So once there is a difference in potential between their ends, those electrons are free to move. They are not really anchored with any specific atom. Each and every one of them can move from one atom to the other. That's why we call them communal, because they belong to the entire community of the atom. Versus insulators, where the electrons are actually anchored basically into their own atoms. It's very hard to move those electrons. You need a huge voltage basically to move electrons for that case. Example of an insulator, for example, is wood, plastic, and air. those are insulators. They don't conduct electricity. Otherwise, there is current already. There is electricity in the wall, and if the air is not an insulator, we would feel that electricity coming right through and through. And but in the case of the clouds, for example, the clouds rub on each other, and there is a voltage that starts to build up over time, and that voltage becomes so huge at some point, the charges will break the air and find their way basically to the ground through the lightning. So in this case, there are some times when an insulator can give in under tremendous voltage differences. Otherwise, under small voltages, an insulator like this one will not give, and that is basically what lightning is. Now, in the case of conductors, I'm going to take a few examples, and here the most common one that we use a lot is actually copper, and also we use sometimes other metals, like they're very poor conductors, but we use them sometimes for small applications like iron, for example. But silver is actually another one, and gold is another one also. Gold is Au. So basically, those are some of the common conductors, but by far the biggest one that is used in industry is copper. So in this case, basically what you put them under a difference of potential, and then the charges start moving. But they don't really move freely like that. I mean, they're actually. Let me get a little bit more screen in here. That way you can. An electron on its journey, basically here is a picture of what a conductor looks like, okay? So basically, this is just a portion of it. This is not the entire wire. This is part of the wire, and I drew it very big. So what you do in this case, you apply voltage on one side and a voltage on the other side. Like, for example, bring a battery to 1.5 volts, and you put it between the ends of the wire. So now the one end is, let's say, for example, 0 volts, and the other end is 1.5 volts. So in this case, the current starts to move. Actually, if this is 1.5 volts and this is a lower potential, the current starts to move this way. So there is a current that starts to move in here. So basically, charges start to move, and start to move in this case. But they will encounter atoms in their way from one end to the other, and that slows down them, if you wish. So an electron moves in, hits an atom, then bounces back, and then moves in, then hits another atom, bounces back, and then hits and move on until it makes its journey all the way through. The atoms, or basically not the impurities or whatever you have in there, and the atoms themselves, they are not sitting still; they are moving back and forth. Mr. Ohm came up with a law that basically boils down to the following: that the voltage across, the difference in voltage across, which is basically V2 minus V1, that is what that is. So it's a difference in potential, is equal to a property of the material times this current. So I can find the current that flows in a portion of a wire if I know its resistance, and this is the difference in potential. Which is the voltage, which is what you usually hear about, 120 volts or 3 volts or 2.5 volts or 1.5 volts, whatever the value is. The car battery, 12 volts, or if it's at least needs 12 volts to operate in the normal circumstances. This is the resistance. The higher it is, the more resistant that portion of the wire is. It depends, of course, on the properties of the material, if it's copper or something else, but it also depends on this cross-section, A. And it depends also on the bigger the cross-section, the easier for the current to flow through. Because you'll have a wider range of space where the charges can move through. The narrower, the more difficult it's going to go and flow through that. Or do I have it backward? I think, hold on, I think rho is, I think I may have it backward. Okay, let's see here. Okay. The expression might think that it's correct, okay? Let me, R is equal to rho times L over A. Yeah, that's correct. Yes, yes. The bigger the A, the smaller the R. The R. The longer the L, the higher the R. So if it takes a very long wire, for example, to run through, of course, it's going to hit so many atoms back and forth, back and forth, back and forth. By the time it reaches the other end, it's basically slowed down dramatically. Versus if the wire is short, it hits a few and then it's on the other side. So the longer the wire, the more resistance you're going to encounter. The narrower the ending, of course, it's like a water hose, basically. If you run a lot of water through a narrow hose, it's not going to go as much as if it's an open area. I hope this explains it. Of course, I only remember the math of it, and usually when you remember the math, it's easy to explain it later on. So this is basically the formula for the rho is actually a property of the material itself. This is what makes the difference between copper and, for example, iron and silver and gold and other different metals. So that is the one that is, for example, for copper, it's a lot smaller than that, for example, of iron. And silver is better than copper, and gold actually is the best material because its rho is very, very small. In other words, has less resistance. It's a better conductor, actually. In case of a wood and other different materials, their rho is so high. I mean, there is just so much that you cannot really, like air, for example. So those are very high, highly resistive materials. Of course, in addition to these two types of materials, conductors and insulators, there are also semiconductors, which are actually insulators. They don't conduct under normal circumstances, but when you add, and they are mainly germanium silicon, those, if you add the right type of impurities to them, they become basically conducting one way and insulators in the opposite direction, hence the word semiconductors. And they're used in logic a lot. For example, in computers and things like that, you will find semiconductors a lot. And then in addition, there are superconductors. Superconductors, they basically conduct electricity with no resistance whatsoever, with no heat whatsoever in them. So those are the things of interest to us. So the biggest thing that comes out of this is this law that we're going to check today. So the purpose of this lab, again, so that you know the objective, is to understand or to explore this law, Ohm's law. So this is the purpose of what we're doing in here. We want to understand the higher the resistance, the less the current, because you can express it this way. And that's why sometimes it's a good idea to put this one in terms of words. V is equal to, I is equal to V over R. So if you can afford, let's say, for example, 1.5 volt, that's the battery you can go and grab from Walmart, you pay for it. So you have this battery, it's a 1.5 volts. What is the current you're going to run, for example, on a 60-watt light bulb or a 100-watt light bulb? Of course, each one of them comes with its own resistance. It turns out the 60 has more resistance in it than the 100, and but one of them has a different resistance than the other one. Hence, the current will be higher in one than the other. So you would want to get all of these things in here for you guys. Of course, we're not doing any of that. We're doing a lot simpler lab than this. The higher the resistance, the lower the current. That's basically what you need to come up from this one. At the end, in the end of the lab, you're going to be drawing this graph. And the graph basically would look like this. Okay? The resistance is R. I think it's going to be 1,000 ohms. And which brings me to the point of what are the units. And this is going to be the voltage, and this is going to be the current. It's clearly going to be some line like this one. So that is basically what you're going to be plotting in here. If I were to draw the current as a function of the voltage, again, it's going to be another slope. This is, I'm sorry, this is slope of another line with the slope in this case, which is 1 over R. Okay, the resistance in here that you guys have in this lab. Okay, so that's one of the graphs that we'll be focusing. So this is in a nutshell. Basically, what we're doing in this lab, we're verifying Ohm's law for different kinds of configurations. Okay, so what we have in the lab, actually, we have first of all, we're going to be measuring the resistance. So that's one of the things that we'll be doing in the lab. So the units that you guys use for this one, the current is measured in ampere, A for ampere. The voltage is measured in volts, actually. and the resistance R, you're going to use the unit for it, which is the ohm. This is the symbol for the, it's like the omega, the capital omega, which is the Greek letter, and it's called ohm, okay? So basically, those are the units. And then before I turn into the lab instructions, let me give you part of the lab, which is a big deal now, which is going to be also another objective in this lab. You have, let's say, for example, one resistance. The symbol for a resistance in circuits is like this one. In this case, we're going to call it R1, okay? And you have another resistance which you bring with you, and you're going to call it R2. Let's say, for example, one of them is 100 ohms, and the other one is 270 ohms. Let's say, for example, this is 270 ohms, and this is 100 ohms, okay? And now you connect, let's say, for example, for the sake of argument, the first one to a 6-volt battery. So you take 100 ohms, and you connect it to a 6-volt battery. So basically, in this case, there is a current that is going to run through it. Of course, the numbers will be given to you, so you don't have to worry about that. And then you connect the 270, you're going to have a different current through it. Now, if you connect the two of them, you have two options that you're going to connect them. Either you connect them in series, which is you're going to verify in this lab. So you take one resistor and you connect the end of it to the other resistor, and this is called the series. And, or you take the two resistors, the first resistor, and you put it next to the other resistor, and you don't connect them one after the other. So basically, you connect this end and this end. So in this case, they're called in parallel. So this one is called series, and this one is called parallel. So that's in a nutshell, basically the theory that you guys probably have done in lecture or will be doing in lecture. So let's get into the, do we have any questions, or should I get into the instructions now and go through the questions? Okay, Micah doesn't think so. So let me take the attendance quickly, because I think we're missing 3 people, actually 4 people. Okay. So basically, let me get into the instructions then, which is really what matters in this case. So here it talks about Ohm's law, what I was just talking. This is the law that we're going to be checking. V, which is the voltage, it's really a difference in voltage, okay? The voltage is like height. What matters is not the actual height. What matters is the difference of height if you want to do work in the case of mechanical systems. Same thing in here. What matters is not the actual voltage. When they tell you it's 120 volts, it's actually the difference between the two ends, because you guys know in the wall there are two holes basically, and when you plug both of them, the difference between the two ends is 120 volts. It's not like this is 0 and this is 120. This could be 47 and this is 120 plus 47. So what matters in here is the difference between the two ends. Okay, so that's the volts, that's the V. The current, which is I, is in amperes. That's the unit for it is called amps, it's amperes. And which is the resistance, it's in ohms. And the symbol for it is that capital omega, basically. So this is the law that we're going to be using. Before we do that, we need to really learn about the multimeter. Let me go back into the other screen to show you an actual multimeter, because this one is actually a drawing of what the multimeter looks like. So let me go back into the other screen. I pulled it actually, I was trying to buy one actually from Amazon. And I got the picture for it. What happened? Oh, it's on the top. Okay, so this is a multimeter now. Basically, if we were in the lab, this is a device that you really need to be familiar with, especially if you're going to be teaching in middle school or high school or anywhere where they do science stuff. You'll have this device in your labs in there. You're going to be doing, and basically in any kind of medical situation, also probably will have something laying around in the electrical room or something like that. So this is an important device that you really need to be familiar with, and we will need this one for our lab. So this is the COM port. This is basically the ground. And from here, you're going to be measuring either currents on one side. So this one can be used to measure current, in which case it's called an ammeter. So measuring amps, basically. If the current is in very small, you use this end. There are two openings, basically, two leads that that connect to it. So one of them is always in the COM port, no matter what. You're going to put one in here. So in this case, if you are measuring the current, depending on how big the current is, if it's small current, you use this end. If it's a big current, you use this one. Usually you start with a big current, and if this device doesn't show you anything, you move to the small current before you basically blow the fuse in the back. Okay, I'm sorry. So probably I should use a big pointer in here. Let me see if I have a pointer in here. Somebody is saying that they don't see the, do I have a, no, I'm sorry. So let me use the draw tool so that to draw on top of this picture. Okay, so let me use a different color. Okay, so this is the one that I was talking about in terms of the ground being the one that you usually connect to it no matter what. So one of the two leads need to go there. Now, if you're measuring small currents, this is the one that you're going to be using. If you're measuring higher currents, this is the one that you need to use. If we're doing the lab, we always start with this one and then read in here. If there is no reading on the current, then we will go to the smaller one. So this one is used now on this side as an ammeter, measuring the current. There are two types of currents that you're going to be dealing with. Either you have this current type, so you need to move this dial all the way here, okay? Or this type of current. This is for the normal DC current, like a battery, for example. This is for the alternating current, like for the one coming from the wall. So this is the one, the dial where you need to put it. Otherwise, you need to put it back in the off position, okay? If I'm measuring anything else with this multimeter, I still need to use this one no matter what, but then the other lead needs to come in here. Now, it depends. I could be measuring the voltages. This entire area is for the voltage. Or I could be measuring the resistance, which is this area. So if I'm measuring in here, this is called the voltmeter. It's the same device. It's called the voltmeter in this case, and here it's called an ammeter. So it's a voltmeter here, and here it's an ammeter. Or it's actually called an ohmmeter if I'm measuring the resistance, okay? So there are three different things that needs to be done in here. Of course, there are other settings in here, which is the three main functions of it are either an ammeter, and there is, I think, a question in there or something, or a voltmeter, which is in here, or an ohmmeter for the resistance. Now, the voltmeter also has the DC voltage and the AC voltage, because the current can be direct current, can be steady, or an alternating current, like this one in here. The picture shows you it's an alternating. So depending on the type of current that you're going to put it either here or there, depending on where you are. Notice also that there is a scales in here. Let me try to remove some of these pictures to see the scales I'm talking about in here. Remove everything now here. Okay, so if you go back into my drawing tool. So this is 20 amp for the DC current, 200 milliamp, and 200 microamp. In the case of the voltages, 1000 volts. Here I have 200 volts, 2 volts, or 200 millivolts. In the case of the ohms, and that's the question that you're going to have all of them in the lab are about this one. So it can be set in the 200 ohms, 2000 ohms, in this particular device, okay, and they differ from one to the other, okay, depending on their application. 2000 ohms, 2 kilo ohms, 20 kilo ohms, that is, 200 kilo ohms, or 20 mega ohms, 20 million ohms. So as you move from one position to the other, the digits in here change. You will have either a lot of digits or no digits at all, or it's an overload. If the resistor is too big and you're putting it on a too small of a scale, it tells you, hey, I can't measure that. It's too much. Okay, that's an overload. Or it can be if it's too small and you put it on a big, it's going to give you 0 because I'm not seeing any resistance. You're putting on 20 meg and the resistance is 100 ohms. So it's going to give you 0 ohms because 0 times practically is 0. 100 ohms is practically 0 in front of the 20 meg. So that's basically in a nutshell how the ohm meter works. In the case of the current, the ohm meter needs to be in parallel with the circuit. I mean, in series with the circuit. So in order for you to measure the current, you have to place, what is the circuit? You have to place it here. Or here, anywhere on the in series with the circuit. That is if you're measuring the current. If you're measuring the voltage, which is this side, anywhere DC or AC, it has to be itself. You have to put it in here. For example, if I'm measuring the voltage across the resistor. Now, if I'm measuring the ohm meter, neither. Not parallel, not series. What you do in this case, you take the resistance by itself and you plug it directly with no power source. And that's the case basically in how you do that. So that's basically the theory that he's talking about in here of how this works. Again, this is a representation of what an ohm meter looks like. Okay, let me stop the sharing of that screen and come back to this screen. So now we're in the PDF, access to the PDF, basically the instructions for the lab. So again, these are the functions that I was talking about in here. Okay, what is the comments? So again, this is the DC and the AC. One of them is voltage, one of them is current. This is the DC and the, the AC and the DC, one of them is voltage and one of them current. Again, AC and DC voltage, AC and DC current, okay? For some reason, it sounds like we're doing music in here, or that's some AC-DC group or something like that. Anyway, and there is the other function that you guys see in here is the resistance also, okay? So that is as an ohm meter. So those are the basic functions in here. In other words, either I am measuring the voltage, or I'm measuring the current, AC or DC in either case, or I'm measuring the resistors, it doesn't matter. In that case, I don't have power supply. I don't have to worry if it's a DC or an AC current, okay? Now, this is basically a representation, a graphical representation of this, how it looks like, okay? Again, I was just showing you that. This is the COM port. This is the voltage, or if I'm using it as a voltmeter, or an ohm meter, I have to have the red in here. And if I'm using it as an ammeter, I have to use it in here. Again, this is the multipliers that you have in that case. Remember that, and some of them, they could go all the way to 200 micro, whatever that measurement is, whether it's an ohm or a voltage or a current or whatever. Same thing, you have a milli, a milli. Or a milli again. Here, it's the level of precision that you're moving. It's all of it divided by 1,000. But the level of precision in here, it's picking up more digits than in here, okay? Same thing in here. I don't multiply by anything, but what happened in this case is, again, the precision starts to increase. Here, with the K, I'm multiplying by 1,000 because whatever reading is 1,000 times. And then here again, I'm picking up more precision in here than, for example, in here, more digits if you wish. Same thing with the M in here. Whatever reading the multimeter is telling you in here, in this digital display, you either divide or multiply by this number, depending on the setting where you have. Because in these regions in here, for example, there are subdivisions that you need to be aware of, trying to pick up the reading in there, okay? So, the question in here is the instructions basically. For example, you have set it on 20 kilo, and this is the reading in here, 3.78. But if you read it, because you multiply that number by 1,000 to get that reading, but if you set it on a different number, here is basically the same resistor. In this example, it's 3.78. That's what the scale is reading on the multimeter itself. If I put it on 200 by itself, it's telling me it's an overload. It's too big for me to find out, because this 3.78 is a huge resistor you're putting in there, and the setting is too low. So in this case, it's saying it's an overload. You put it at a 2K, and it's still also too overload, because this is too bigger than even 1,000 ohms. You put it on a 20K, now it's giving you a reading in a sense that it's telling you it's 3.78. You multiply that by 1,000. So if it's a 20K, you multiply it by 1,000. So in this case, it's going to tell you, hey, it's 3,780 ohms. So in this case, that's you have 3 sig figs in here, because this 0 is not a significant figure. So in this case, you have a good enough sig figs. But if you put it on a 200 now, it's telling you 3.8. Again, for 200K, you multiply it by 1,000. Once you multiply it by 1,000, 3.8 multiplied 3,800 ohms. So this is fine. But in this case, you have less sig figs in here, basically. You have only 2 sig figs versus the first one. So in other words, these readings can be basically give you a lot of precision, and this is your best setting. So the question that is on the bottom in here, what does it mean to say that the meter is on its best setting? One, it's basically giving you the highest number of significant figures. That's basically in a nutshell the answer to that question. Okay, question 1. Why is it important to always check the meter to make sure that it's always its best setting? Because either it's an overload, it's not basically reading, or it's not, it's too small. Like in this case, it's giving you a 0 value because it's not completely sensitive to it. So in this case, you would want it to be in its best setting, because then the data that it's giving you with the highest precision possible. So that's the answer to the second question. Which settings are best suited for each resistor? Now, this question 3 you may skip. So this question 3, you cannot answer it because we are not doing the actual lab in class to really be able to say this is or that one. So basically we have, in the lab, we have a brown and a red and an orange and a yellow and a blue and a violet. Basically the casings themselves are colored. The resistors themselves, they have their own values, and they all look the same actually, if you're not too careful. But they're color coded actually. The actual resistance are color coded, and each color means something. And this is not the one that I'm talking about. This is not the color. This is just for our own lab. We put them in a casing that has these colors. But there are bars on each resistor, and each one of the bars means a value. And if you work out the numbers, you will find that they will come out to be around this number. So when he tell you it's 100 ohms, and you go to the lab and do the actual measurement, you may find it slightly more or slightly less than 100 ohms. Because again, that measurement device carries with it an error. And again, those standards, they change, and the resistor might have a different value than what the 100 ohms. So probably the reading will be 98 ohms or 107 ohms or 103 ohms or something like that. So it could be slightly different. I mean, probably not correctly for this one. Maybe it's slightly off, but basically that is within the margin of error, because again, those two numbers are not really, how should I put it? They're not significant. The only significant thing in here is one. Like 270, probably you're going to get 272 or 268 or something like that. Then there is the 470 ohms, 1,000 ohms, 4,700 ohms, and then there is a 10K ohm, 10,000 ohms. So those are the resistance we're going to be doing for in this lab. Now in here, it tells you to connect it. So basically this is what you do. We have a big power supply in the lab. You bring it, and then there are different settings for it in here. You can set it that, because this is a DC source now, 6 volt, 12 volt, depending on the thing. And then the dial, you can change the values from 1 volt to whatever value you want to, all the way to 12 volts or something like that. So this is your battery. The current will lead from here, the red, and comes to this ammeter. So it's a multimeter device now. In the opening, it's the same device. This one and this one are the same. They're the same, I mean, different, the same type of device, basically. Both of them are multimeters. But this one is operating between the COM and the amp, so it's an ammeter. This one is between the COM and the voltmeter, so it's acting as a voltmeter now. So this one is in parallel, basically, and this one is in series with the circuit. So the current comes in here, goes in here, and comes out from the COM port. And now it enters in here, and it says two things at the same time. It says the resistor, which is this one, and behind it, the multimeter, and they're both connected to the same thing. So the current actually was split in two. Part of it will go through the resistor and come out in here from the COM, from the other side of the resistor, and the other part goes to the multimeter and come out from the same port. So basically, the current splits in two ways and merges back in the same point. So once this merges back, now it's going to come here and go back to the power supply, and basically the battery will push the charges again this way, and there is a steady current in this circuit. So I'm going to stop sharing the screen to show you how the activity would look like, at least before you start filling in the data in here. So there are some data in here we have to do. We have to come up with some numbers and answer the questions. So the voltage in here is, so let's go and get the data first. I'm going to stop sharing this thing in here. And if you go to the lab, let me show you what it is so that we have a, so that you know how to access this one on your own. Lab, is this the one? I think it is. This is the message I sent earlier, assignment. Are you guys seeing the same screen I'm looking at, namely for the assignment and everything else? I'll make sure before I start talking and then realize at the end. Okay, very good. So the lab we're doing right now is lab 9. Okay, very good. So it's lab 9. And the instructions for lab 9 are here. So you will need to come here and click on one of these links. The first link is the one that is going to get you the first set of data. So I'm going to click on it, and it's going to open something on your browser, and that is a GeoGebra that I talked to you guys last time about. So wait for it until it loads, because it does calculations behind the screen. And in here, basically, it's the same graph, the same basically setting that we talked about earlier. Basically, you have the Pasco interface, which is really your power supply, and then going through the ammeter, then coming from here, the current splits between the ammeter and the resistor, and then merges back at the end, back to the power supply, and closes the loop, basically, so that there is a steady current running through that one. Right now, the voltmeter is reading 5.98 in here, so I really need to recycle these numbers a little bit to make sure I run the experiment for my own data. So right now, the voltmeter is reading 5.91 volts. So I go back into my PDF file, so I'm going to stop sharing the screen right now. I'm taking this data now as part of my table. I'm going to stop sharing the screen and go back into my table, the PDF file, share, and put in here 5.9, whatever that thing in there, okay? The volts, okay? So that's how much volt I have in this case. Now, if I go back into, let me stop the screen in here because I need to get my current in here and the resistance in here. Let me just stop in here. I may have to change this thing in here a little bit to reflect the actual lab. But the instructions, like I said, are slightly different in here. Okay. The current running through the brown is 29.58. The current running through the red is 21.92. So basically, the different currents in here for each one of these things is given to you. That's what the second multimeter is giving you. So basically, you put one of them. You put the brown, and you get the current. But this 29.58 is not amps. It's milliamps. And a milliamp is thousands of an amp. So this number has to be divided by 1,000 to really be placed inside that proper thing. They have the brown, the red, the orange, the yellow, the blue, and all of the numbers. So I go back, stop the sharing in here quickly. So go back into the other file in here. Share the PDF file. So put whatever that number and current section in here. The resistance in here, you're going to put the values that were provided for you, which is the red 270 ohms. So if the red is 270, the brown is 100 ohms, and so on and so forth. Now, if I multiply these two numbers by themselves, it should give me a reading now for the current, okay, for the voltage. Of course, I'm going to come up with an error, and the error can, if you guys have difficulty with calculating of the error, or should I probably include the instruction on how to do the error? All you have to do is take this voltage, subtract from it this voltage, and divide by this voltage, and that should give you how much error percentage you have. The difference divided by one of them, which is the voltage that you have in there, and that should give you the error. At least in a nutshell, do you guys understand how this process works? But you need to run that experiment at least once or twice before you actually get your numbers in there from the link. Does this sound good? Or should I include more examples? Yes, no? Micah just answered. Okay, good. Okay, so basically we have an understanding of how that works. So if there is a problem, you guys need to, basically what I'm doing there is simulating the actual lab without actually having to do lab, which is kind of a really something I hate to do, but that's basically what we're doing right now. Okay, so we're done with that part. Let me stop sharing this screen and go back into the, oh, I'm sorry, we still need this screen. What is it? So basically we did the first part, and here were you able to get some more errors? If you did not, basically blame it on the simulator, okay, so for your case. Okay, complete lab 3, calculate resistance also times and calculate the percentage. Were you able to get small errors from your plot? I'm going to show you basically later on. Basically, I'm going to, I may have to include another video with instructions basically on how to do the plotting. But one of the questions that basically you guys run into is how to plot these things and how to get these numbers and put them on the graphs. Okay. So the second part of the lab so basically we're doing now at constant resistance. Let me check first of all to make sure that I get everything in here for this part. Yes. Okay. So it's still the same link in here. So let me stop sharing that one and go back to the same basically link to show you how to do the second one. For the second setting, basically the resistance now is 1,000 ohms. Think of it that in here we put already the 1,000 ohms, which is, what is it, the yellow? We put the yellow in here already instead of putting any of the other colored things. And then now we're running the current. When we run a, let me run the experiment several times before I make sure that I have in here. So the voltage now settings is 0.98 volts. That's what this guy is reading. And the current is 0.97 amps, milliamps. Don't forget that you're supposed to multiply by 10 to the negative 3. So this number is actually times 10 to the negative 3 to get it really correct, okay? So because this is in milliamps, all of this measurements for the current are in milliamps. Basically, this is this one in here has to be on detecting that much small currents in here, okay? Again, when we moved it to around 2 volt, this is what we get and what we get. Now we have a different plot that we're going to draw for this one in here. Namely, we're going to draw the current as a function of the voltage. The slope should be 1 over 1,000 or something like that. So that's basically but your slope may be different, okay? Because of the fact that your random numbers change for you, so you may end up with different set of numbers, okay? Please do not take the first reading from this one, and don't change the file. If you change it, you might end up with a lot of basically different stuff. So if in case you change it, of course you cannot change it on their website. It's going to be messed up for you. So probably you need to come back and click on the link again and come back to it with a fresh set of data so that you have the new lab again set up based on the default values that I already put in there for you guys. So that part is done. So let me stop sharing the screen again. Let's go back into the instructions. Now we're going to take resistance, 3 resistance, the 270 ohms, the 470 ohms, and the 1,000 ohms. We're going to take the red, the orange, and the yellow basically resistors. And we're going to put them one after the other. Basically take one, put it next to the other. So this one starts from here. Its end starts the beginning of the second one. This one, there is nothing attached to it. And then from here, the end of that second one is the starting of the third one. So basically, if I connect a battery, I connect it from here to here. So the current, as it leaves the battery, basically comes in from here, goes through this leg of the resistor, comes out from this leg. I cannot go in here because there is no nothing in here. Oops, Control Z. So now it's going to come out from here, come through this leg in here, and come at the end. So basically, I have this resistor with this resistor with this resistor, all of them one following the other. So this is called the series. Or what I can do, I actually can connect the battery in here to this setting in here. The current comes in here and splits itself between this resistor, come down, or this resistor and come down, or again this resistor and come down. So this, in this configuration, basically what you have a parallel configuration. 3 resistors there, one on top of each other, basically parallel to one another. The current in one resistor is not the same as the current in this resistor, is not the same as that current, that resistor. So basically the current, let's say for example, 10 charges leave the positive terminal of the battery, they come in here, they have to decide. They cannot all go in one direction, so we say, okay, 5 of you go here, 3 of you go there, and 2 of you go there. So when they come back in here, they will all meet again so that they come back to the battery, so that 10 left, 10 came back. This is the conservation of charge, which is one of the fundamental laws in nature. Versus this case in here, where the current in here comes in, and 10 amps, 10 coulombs, for example, 10 charges come in here, they all merge from this resistor together. So they come in here and they all merge from this resistor together. So the charges or the current is the same in the series. So in the case of the series, the current or the charges are the same. I is the same. Whereas in this case, I is not the same. But the voltage drop is different. In here, let's say, for example, we have, for the case of argument, we have 10-volt battery. So let's say, for example, we drop, let's say, 5 volts on the first battery, we drop 2 volts on the second battery, and we drop let's say, for example, a 3 volts on the last battery. That is our overall drop of 5 volts. I mean, 10 volts, that is basically like a mountain, basically, coming down from different, with different heights, basically. The overall height is 10 meters, but you can come down this much height, and this much height to combine for the 10 meters. But in here, the drop is the same. They're all basically, they come in here and they drop off, but they split themselves and then they come in here. So the voltage actually is the same in here. So in the case of parallel, the charges are the same, or the current is the same. I'm sorry. In the case of series, the voltage and the charge, in the case of series, the charges and the currents are the same. In the case of parallel, the voltage is the same. So that's basically a big distinction between the two. So in the case of the series, this is the law we want to check. When you put resistor after resistor after resistor, the overall resistor, as if you have one resistor, which is the sum of all the resistances. So we need to check that law. In the case of the parallel, the effective resistor, basically the resistor, as if it's the inverse of the sum of the inverses. This is one of the laws that is that you guys are going to be checking in this part of the lab. So we're going to check this one to see if it's true for the case of the parallel. We're going to check this one to see if it's true for the case of the series. So let me go back into the activity now. It's a different activity now. So let me show you first. Let me stop this screen and go back into the share with you guys the lab. So it's part 2 now. So I'm going to click on part 2. So this is the second GeoGebra link. So it's going to open a new link for me on GeoGebra. Again, I have to wait for it to load. Again, don't take the first values. Basically, you have to at least redo this one in here. So now the readings of actually the resistance, these are not the nominal values that we have in there. The 270 is actually 268 after I run it a few times. For example, I might have different values close to probably what the lab is. So again, run it at least a few times and then collect your numbers. So R1, the first resistor is 268.38 ohms. You don't have to go to this high precision, okay? It's 269 ohms. This one is 468 ohms, and this one is 998 ohms. So when I add them up, if I check this one plus this one plus this one, is it equal to 1,735? So if I take the ohm meter, the multimeter now, and connect this end to that end, this is the reading what it's giving me. If I take it, connect it in here between this end and that end, this is the reading for R1 what it's giving me. If I take it this one, just between this ends only, this is the reading it's giving me. If I take the same ohm meter basically and connect it from this end to this end, this is how much it's giving me. And if I connect them, all three of them together, and connect the ohm meter now from one end to the other end, this is what's giving me. So I need to check now if I add all of these numbers, is it true that the R effective or R total is the sum of all of these three R's? Obviously, probably it's not. Maybe it's off a little bit. Okay, that's one thing. Now, the same thing. I already measured the R1 in here. Here it is. I already measured the R2 by itself. Here it is. I measured the R3 by itself. Here it is. When I connect all three of them in this way and connect now the multimeter from one end to the other end, this is the reading it's giving me. When they are in parallel, apparently, the resistance is smaller than any of them. It's effectively less than any of this one combined. But if I put them in series, it seems like the effective resistance is bigger than any of them. Actually, it's the sum. Okay? So that's basically what this one. Please redo the data several times to have something here before you put your numbers. So once you do that, now you're done with this part. So you come back to your lab in here. Let me go back into the lab. And here is the table. So now the series, first of all, I have the values now. So this is what the series is giving me. This is what the theoretical is giving me. Okay. If I add the three only, R1 plus R2 for R3, this is where I put the theoretical. So this is what the multimeter is giving me. It's the first number, the number that is in series. That's how much it's giving me. If I take the three of them now and put them in series and do the calculation, basically take 1 over 268, 1 over 469, plus 1 over 100, plus 1 over 997, and add these three numbers, and whatever I get from the calculator, inverse it again. That is what the theoretical should be. And then what the multimeter is what the multimeter is saying. Again, I can show you how to do the calculation for the error in the later basically instructions, and or actually with a video or however you guys feel about it. So this is your lab in general. And basically you're going to answer whether or not it checks or not. Any questions? Or do you need help more with the math a little bit? Probably in a later video or later instructions or something. Because I don't want you to really waste a lot of time on the math when it's probably not really the objective. The objective is to really have an understanding of the physics. Okay, I'm going to be working on the instructions. I probably will give you more examples of the math. I may even have to come up with a different program that does the math for you. All you have to do is do the math. But like I said, I really want you to focus on the physics and understanding the idea behind what Ohm's law is saying, basically, and how this thing works, and have a feel for what resistance is, what current is, what voltage is, and so on and so forth. Good? There is the reactions in here to make sure everything is good. Okay, where can I get a hold? Okay, I'm gonna be working on it. Hopefully, once it takes time for the for me to learn that it was saved. So basically, they save it. I download it and basically go through the whole video and make sure that you guys have it, and then I upload it back probably by tomorrow morning, hopefully before noon or something. That's the question from Desiree. Basically, I'm trying to answer here about when is this going to be available. Okay, link to my YouTube, man. Just go to YouTube and look for DJ Buzidi, I think. Or otherwise, I'm gonna. Yeah, it's a good idea to. I'll put it on you on Canvas. How's that? Okay, that's Micah's question. Okay. Okay, guys. Have a good rest of the night. Unless you have any questions for me or something else. And I'm not gonna be seeing you a week from today. You guys know that. So a week from today there is no lab, but I will see you 2 weeks after that. And also there is a change in the labs. There is a potential that we're going to lose one lab, okay? So we're probably not going to do all 13 labs, but probably we'll just be able to do 12 of them. Thank you, guys. Lab 9 and the due dates are all on Canvas. I changed them. I'm trying to work around your exams. That's a question from, I think she goes by a different name than Rizal, okay? So the due dates are on the labs, okay? Or on Canvas, I'm sorry. No, we can't skip lab 10. Actually, lab 10 is still there. And actually, we have to exceed number of 10 for you guys to drop another lab. So at this point, we are only dropping one of them. That's a question from Martin. Okay, guys, have a good night. And be safe, please. And keep in touch. Thank you. Bye.